Hi everyone, welcome to Conference 42 Observability 2025. My name is Vamsi Krishna and I work as a senior software engineer at Walmart, where I primarily work in infrastructure engineering. And today I will be presenting on cloud native observability, building visible, resilient, and scalable enterprise systems. So this talk dives into how advanced monitoring and analytics transform enterprise systems in modern day cloud native architectures. So this is a topic which is close to my work on AI-driven API resilience. So the next 30 minutes, we'll explore the shift from traditional monitoring to observability, real-world metrics, the pillars of observability, and practical implementation strategies. So let's get started. So what it takes from monitoring to observability. Let's begin with a fundamental comparison. Traditional monitoring focuses on predefined metrics. So think about an CPU usage or a request counts, which are limited, have a limited context. So now we need to, which collects, displays, and data from specific sources. It often creates silos where teams see disconnected components, leading to reactive fixes after users are impacted. Reacts to predefined alerts or thresholds notifying users when something is amiss. Contrast to this, we have a cloud native observability. It gives us a holistic view through metrics, logs, traces, unifying visibility across microservices. This enables proactive detection. So just imagine catching a latency spike just before it affects users, and faster root cause analysis, which is critical in distributed systems across the industry with this kind of high volume traffic. So, what is the relation between the observability and monitoring? So, observability can be seen as an extension of monitoring, where monitoring provides the data and observability provides the deeper insights and understanding. Monitoring is a necessary component of observability, but observability goes beyond the scope of traditional monitoring practices, enables us for proactive investigation and resolution of issues by analyzing them as a system behavior and identifying root causes. In essence, monitoring tells you when something is wrong, but while observability tells you why and how to fix that. So now let's see some real world implementation metrics. So these are some tangible results. Practical implementation has delivered a 40% faster resolution time for incidents, which is down from hours to minutes, thanks to the correlated data. And studies show that 25% resource efficiency is achieved by optimizing infrastructure utilization, directly impacting 35% of database load reduction. And what about the detection speed? It's almost around 200 milliseconds, which is near time anomaly identification. And it supports 58% faster incident detection goal. These metrics come from production systems handling complex scenarios during Thanksgiving, Black Friday, and holiday traffic peak times. So these stats rely on tools which are pulled up from Dynatrace and GCP Stackdriver. So moving on next, we have few pillars for observability. So let's observe this triangle. Every small triangle is important to get the details from an atomic level to an holistic point of view of an application. So observability rests on these three pillars: metrics, logs, and traces. What are metrics? So metrics are quantifiable. So think about a latency or an error rates that are tracked in real time. So these are your system's vital signs. Logs are timestamped records of events and errors, offering a detailed audit trail. For instance, in a microservice failure, logs pinpoint to the exact state change and also pinpoint to the exact line of code which went wrong. And moving on to the traces, these are like this is mapped from end to end request paths, revealing dependencies, broad bottlenecks. So in the distributed setup, a single request might span around to 10 services. So these traces help us see the full picture. In API resiliency work, Prometheus is used for metrics, ELK for logs, and Jaeger for traces. This triad enables to proactively manage 85% faster issue resolution which is a key metric for enterprise scalability. And now let's see how it behaves in a stateless versus stateful services. We need to differentiate between the observability in these two services. So what is a stateless services? Think about load balanced APIs, which focus on throughput, latency, and ephemeral resource use. So we monitor these with horizontal scaling in mind. So the benefits of these are simplified scaling, easy to troubleshoot in case of an individual issues. So now, whereas coming to the stateful services like databases, which require tracking persistence metrics like replication health, consistency, and storage performance. So for an example, in a Google Cloud Spanner, we ensure that the data durability is across multi-regions. The benefits of this are users experience continuity in their usage. It's a rich personalization and potentially more complex features when all these get added. And coming to observability strategies, they may vary notably between stateless and stateful services due to their differing approaches to the state management. Stateless services, which are easier to scale, demand greater focus on tracing individual requests and analyzing errors, in contrast to the stateful services, which require a broader view that captures persistent state and ensures session continuity. And now the shared patterns include health probes and anomaly detection. Implementing of these to balance the stateless API performance with stateful database reliability, it will support us in 25% of latency reduction. So this dual approach is critical for hybrid cloud native systems. And then comes the distributed tracing implementation. So what is this one? So distributed tracing is a cornerstone of observability. First, instrument your code. Add a traced context propagation using libraries like OpenTelemetry across service calls. Next, configure intelligent sampling. Capture 100% of critical paths, but just as a side note, do not sample a lot of traffic. Just sample the data which you want to do it. Say 1 in 1000 requests. So we need to include both normal and exceptional patterns. And then centralize the pipeline with a scalable infrastructure. Think about something as a Kafka or a GCP PubSub to ingest all this data and trace it out. So these process millions of spans. And finally, perform the root cause analysis, visualize traces in Jaeger to spot bottlenecks because these ties directly to your 85% resolution metrics from studies at an industry level. So another key topic is API Gateway Observability. So what is that? So API Gateway Observability refers to the ability to monitor, measure, and gain actionable insights into the behavior, performance, and health of API traffic as it flows through an API gateway. It helps ensure that the APIs are reliable, secure, and performant. But now, why exactly the API Gateway Observability matters? This acts as the entry point for microservices in distributed systems. The gateway is where the request ends from the external world to the internal world. So the API gateways are observability hubs where we can get traffic insights, request volume, service dependencies, and rate limiting effectiveness. So these traffic volumes could vary from managing few hundred requests per second to tens of thousands of requests per second during our peak times. And this provides a centralized control plane for routing, authentication, rate limiting, and caching. So what does observability enables in the API gateways? It gives us real-time visibility into the API traffic, issue detection, whether it might be latency, errors, anomalies, auditing and compliance, and also security monitoring. So when I say security monitoring, that is the key. It monitors authentication events and attack patterns, which we can give them to the InfoSec team. Hey, these are the attacks coming up. So there are a few other performance metrics like latency and throughput, which are very critical. So 25% latency reduction could be achieved by optimizing gateway routing. which is a direct application of this particular slide. So API gateways, native observability. What is that? So how can we achieve that? So we can do that by Azure API management plus some application insights, an API plus a stack driver, or Kong, Nginx, Istio, Envoy with Prometheus and Grafana. So these are the tools, and there are like other tools like GCP API Gateway with integrated monitoring dashboards. Makes this actionable. So are there any gateway specific challenges you are facing? Let's see, yeah. So best practices include enable structured access logs with correlational IDs. So these IDs help us relate from an end-to-end monitoring of what happened for that particular request, and also use rate limiting and circuit breakers with metrics exposure. Instrument your API gateway with tracing headers, which includes request ID and also transparent. Monitor latency percentiles such as P50, P95, P99 for the SLO enforcement. Track end-to-end transaction paths using distributed tracing. So moving on next, we have an observability pipeline design. A robust observability pipeline has 4 stages. Collection gathers telemetry from services and infrastructure. Think of agents in this case on each and every node. Processing of normalization and filtering data. So stream processes are used to reduce noise, to keep only critical signals for a few hundred milliseconds detection speed. That's as an example. So this is a kind of filtering out the additional noise or to pull out the exact data which we are looking for. And then storage uses tried strategies. So hot storage for recent data, cold storage for archives, which helps us in balancing cost and access, aligning with 25% of resource efficiency. Now, visualization turns data into dashboards. There are many tools like Grafana to spot anomalies in real time, supporting 40% faster resolution. These pipelines become the backbone of our system. And now we have high availability strategies. So what are high availability strategies? High availability ensures minimal service disruption and maximum uptime. From an observability perspective, the ability to detect, understand, and respond to failures is critical to achieving true resilience and scalability. High availability is a non-negotiable in a distributed system. So for that, we deploy collectors and storage across multiple availability zones to avoid single point of failure. So what about the redundancy and failover visibility? We need to monitor at a node level, zone level, and even at region level for redundancy, and track failover events and measure mean time to recovery, which is termed as MTTR in the industry levels. And then alert on degraded clusters or failed availability zones. And now how to monitor across a cross zone or a region observability for a multi-cloud high availability. So these relates to correlate the metrics, logs, and traces across the clouds, detect latency between regions, and audit cross-cloud failover success and data sync integrity. Designed for graceful degradation, which helps us in reduce telemetry if any backend fails. Ensure core functionality. Test this during your peak loads to get all the corner cases, but that might be again our own individual case. If your system behaves well during low periods, then to get all the corner cases, then yes, of course, we can go ahead with that. And then we need to do a local buffering which temporarily stores metrics when any connection drops or a multi-chanting alerts, ensuring teams getting notifications via Slack, email, and also PagerDuty alerts. So these strategies underpin 50% of our downtime reduction, which are critical for enterprise resilience. And now, how do we do a capacity planning and what are the optimization steps we need to perform? Capacity planning starts with an historical patterns. Aggregate all the metrics over the months to understand utilization. Ideal Data in this case spans over 6 months of the API traffic, and then forecast this demand with machine learning. Predict seasonal spikes like Thanksgiving, Black Friday, or holiday day traffic, which helps us optimizing resource allocation. And then optimize dynamically using autoscaling, balancing cost and performance, which helps in continuous improvement of refining these models, aligning approximately 25% utilization of resource efficiency. And now for the continuous improvement, we need to establish a feedback loops to regularly compare forecasted projections against the actual consumption patterns, refining prediction models and allocation strategies. And now what about the implementation roadmap? So let's outline this roadmap. Start with foundational building, set up metrics with Prometheus and centralized logging with ELK, define your SLIs and SLOs for core services. Then move on to the advanced capabilities. Deploy Jagger for tracing across microservices and build custom dashboards for teams. In the optimization phase, add anomaly detection with AI and automate remediation for common issues, which are building for 58 of our incident detection. As per industry research, this phased approach has guided 40% resolution improvement. Plan to start with one service and scale. Always remember, start small and scale. This will reduce the impacts that any new changes. And that wraps our journey through the cloud native observability. We have covered the shift from monitoring, real world metrics, pillars, and implementation strategies. Thank you all for your attention, and I hope everybody enjoyed the session today. Thanks a lot.